Just real quick, guys, before we get started here with this, I just wanted to say, A, I'm sorry for not being there today. I was going to do a lab with you guys, actually one of my favorite labs to do, but obviously since I'm not there, I'm not going to do that. So here's what we're actually doing. We're going to push ahead a little bit to something that we were going to do after we wrapped up the kinematics unit, okay, which is not too far away. We really only have a few more days left of looking at kinematic stuff. And the thing that we were going to do next is talking about vector addition. So I'm going to have you guys spend a little bit of time today, at least getting a basis for that, getting a foundation and doing some of that unit. We will get some more practice with it next week, but hopefully we won't spend as much time on it next week because you guys are getting a head start on it today. It is kind of like a standalone unit, so I don't think it's going to mess things up too much that we're doing it now. But again, I apologize, and we will talk more tomorrow about the schedule moving forward. Okay, so we're going to spend the next little bit of time doing a mini unit here, about a week here, on vectors and linearization. So we're going to dive a little bit deeper into vectors and actually start doing some math with vectors. And we're also going to talk about a technique for analyzing graphs called linearization. Last unit, you folks got a little bit of an introduction into vectors. We talked about how vectors are numbers that have a direction associated with them, and things like velocity and acceleration and displacement are all vectors because they all have a direction. But so far, at least mathematically so far, we've only dealt with vectors that are purely horizontal or purely vertical. Obviously, things are not restricted to that, right? Cars can travel in directions other than just northeast, south, and west. They could travel northeast or southwest or a lot of different possible directions. So we want to be able to analyze vectors that are at angles, that are not purely horizontal or purely vertical. And this is going to help us as we transition into our next unit, which is forces. So here we have a grid with 2 points marked out, point 1 and point 2. And we're going to pretend that this is kind of like an overhead map here of some location. And a person is actually going to move from point 1 here up to point 2. Let's think for a second about what our displacement would be if we took that trip from point 1 to point 2. And we're going to draw a vector representing that displacement. So our vector representing that displacement would go from point 1 directly to point 2 and point in that direction. That would be our displacement as we move from 1 to 2. Okay, now suppose that instead of just drawing that displacement vector, pretend that this is actually a map of Philadelphia, right? Philadelphia is laid out like a grid, thanks to Benjamin Franklin and some others. So this is kind of like an overhead view of some of the streets in Philadelphia. And let's say that we're here at point 1 and we want to walk to here at point 2. Well, how would you walk from point 1 to point 2? You can't obviously take this direct path because there's buildings and other things in the way. So probably what you would do is you would walk 6 blocks to the right or east and then 6 blocks up. You also could go north or up first and then east. It doesn't really matter the order, but let's just, for the sake of this problem, say we go east and then north. That would take us from point 1 to point 2. Okay? Our displacement, however, would still be this direct line connecting the two, right? Our displacement is how far we are from where we started. But we wouldn't walk that actual path. We would walk along this street 6 blocks and then up 6 blocks. It's important to note, though, that these two pathways, our direct line, okay, assuming we could potentially walk that, and our path where we go east and then north, they result in the same final position, okay? They result in the same overall displacement as well. So in some ways, this blue path is equivalent to that black path. Obviously, this is a shorter distance, but in terms of the displacement and in terms of where we end up, it's equivalent, okay? So these two mathematically are equivalent. So, as we just said in the previous slide, if we're walking along that path from 1 to 2, we have a few options. Okay, we can either walk directly from 1 to 2 along that black path shown, or we can walk some distance east and some distance north. All right. And what we're really doing there is we're introducing the idea of vector components. Okay. Instead of walking at an angle, we're breaking it down into walking some amount east-west horizontally and some amount north-south vertically. And we end up with the same result. We end up with the same overall displacement. We're going to talk a lot about displacement here in the beginning of this unit. But this would apply to any vector. It doesn't necessarily have to be displacement. But we're going to end up with the same result. And so what we did, like I said, is we did our vector components. We found an x component and a y component. And what that really does is it represents, all right, the amount of the vector that points in the x direction or the y direction. Okay, so let's say we walked a distance of 100 meters at this angle here, right? This x vector component tells us when we walk that 100 meters, how far did we go east and how far did we go north in that period of time. Okay, so maybe let's say this is a 45-degree angle. Okay, and that would mean that when we walk 100 meters at that angle, we travel 70.7 meters east, where we end up 70.7 meters east of where we were, and we end up 70.7 meters north of where we were. These guys here would be the vector components. And the reason why we're introducing all this, the reason why we're even talking about this, is you're going to find moving forward it is much, much easier to deal with vector components instead of angled vectors. All right, they're going to make your life a lot easier to work with, and in some cases they're going to make problems possible to solve that otherwise would be impossible to solve. Okay, so let's talk a little bit more about vector components. The first thing we're going to talk about is how exactly to draw these vector components. Okay, and I always think back when we're drawing them to that walking in the city example. Okay, thinking about how you could walk from one point to another only by going east-west and north-south. So what we're going to do is when we have a vector at an angle like this, okay, so when we're drawing our vector, we're always going to start here at the tail of our vector, at the beginning, we call that the tail, and we're going to draw our first component. I usually draw the horizontal component first, but you certainly are welcome to draw the vertical component, as you see here. Okay, and so we're going to draw that first component showing how much we go horizontally, or how much of that vector is vertical. And then from the end of that first component, we're going to draw our second component. Okay, draw the vertical or the horizontal, depending on which one we haven't drawn yet. So one really important thing to notice when we're drawing these is vectors should always be drawn tip to tail. Okay, and so what I mean by that is we're looking at this intersection point where our two components intersect. All right, and after we've drawn that first component, we're always going to draw that second component from the tip of the first component, the arrowhead there. We're going to put the tail of the second component and go from there. All right, so we draw a horizontal one. From the end of our horizontal one, we draw our vertical one. Or we draw our vertical one, and from the end of our vertical one, we draw our horizontal one. And they always line up tip to tail. So that's one thing we want to keep in mind. Second, we always want to make sure that these components are perpendicular. Okay, we're always breaking it into horizontal and vertical, so our two components should always be perpendicular. And lastly, we want to make sure that the direction of the hypotenuse of that overall vector matches the directions of our component. So this vector is going to the right and up, which means we have a right component and an up component. No matter how we draw it, we need a right component and an up component. So we have a few examples here of ones that are not drawn correctly. The first one here, we see that our vector is going down and to the left, but our components go right and up. So that doesn't match, that doesn't work. Okay. We have another bad example here. This vector is going up and to the left, and we see our one component goes up, so that's good, but our other component goes to the right. All right. This also shows how they're not lined up tip to tail. That would be tip to tip. Okay, we don't want that. Lastly, this vector goes up and to the left, and we have an up component, which again is okay, but another right component. And we look at how they're lined up tail to tail, and that's not good either. All right, so all of those are not good. we want our vector components to look like these examples here. So we have a little practice here. So pause the video for a second, take a stab at this, and try and draw the x and y components for those three vectors at an angle. Okay, so let's go ahead and go over this. So I'm going to start with this vector here, which is going up and to the right, which means I'm going to draw a component to the right. And from the end of that, I'm going to draw a component going up. We could have switched them around, so if you had gone up first and then to the right, that also would have worked. Moving on to this one, which is up and to the left, I'm going to draw one component to the left, and then a second one up. And once again, if you flip the order of those and went up first and then left, that would also work. And then this final vector here is down and to the left. And so I'm going to go ahead and draw my components. We have one going to the left, one going down. And again, if we switched them, went down first and then to the left, that would work as well. So you don't need to draw that entire rectangle. Either the blue or the red is sufficient. The next thing we want to talk about is naming vectors. So when we get into these vectors in 2 dimensions, there's 2 ways that we can describe them. Okay, we can either talk about our vector components, right, and actually name them based off of our components. So for example, for this situation here, we have 4 meters to the right and 8 meters up, or 5 meters per second west and 7 meters per second south. So giving both those x and y components is sufficient to describe the vector. Just like with our city blocks, we could have said 6 blocks east and 6 blocks north, and that is enough direction to get the person from where they started to where they want to go. All right, we don't need to necessarily know the actual distance from one point to another, or the angle, the heading we sometimes call it. We just need to know the 2 components, and that is sufficient. The other way that we can name it is without the 2 components, we can give the actual distance and give the heading. Okay, so in this case, we're going to give the magnitude of the vector, right, which is the hypotenuse, and that's an important point. All right, we've talked about magnitude before. That's just the amount. So when we're dealing with 2-dimensional vectors in these diagrams here, the magnitude is simply the hypotenuse, just the amount of that vector. And then we can also give the direction, which in this case, what we really mean by that specifically is the angle, is the heading. Okay, so we have this vector down here. And we would say that this vector is 8 meters. All right, so that's the magnitude, and the direction is 25 degrees north of east. Okay, so what does that mean? When we say north of east, we're starting with our east direction, okay, and we're going 25 degrees north of that east direction. So there's our 25-degree angle. We're starting with east and going 25 degrees north. All right, and that's what ultimately gives our heading. So that's what that means. That's how we're going to use that directional component to this. All right, we have another example here, 10 meters per second. That's our magnitude, the hypotenuse, and the angle is 15 degrees east of north. So we're starting with the north direction here, and we're going 15 degrees east of that north direction. All right, and that ultimately gives us our heading. Okay, and lastly, we have 6 meters at an angle of 40 degrees south of west. So we're starting with our west direction, okay, and we're going 40 degrees south from that initial west direction. So 6 meters at an angle of 40 degrees south of west. So that's the other way we can name our vectors. Just a quick reminder here of something that dates back actually to our math pretest, but keep in mind that when we're drawing these vectors, they'll always be perpendicular. They'll always form a right triangle. So good old SOHCAHTOA and the Pythagorean theorem are going to be very much in play here, and we're going to use them as we're analyzing some of these problems. Okay, so let's do a few practice problems here. We're going to start with a few where we're given the magnitude and the direction of a vector. And what we want to do is we want to draw the vector, if that diagram is not already given, draw the components, and then we're going to find the values of those x and y components. And that's where our trig and SOHCAHTOA is going to come in handy. So why don't we do the first one together, and then if you want to pause the video and try the next 2 on your own, that is great. So here's my first vector that I just redrawn over here. First thing I'm going to do is draw the components. So we have one component going up, one component going to the right. And I'm just using the angle that I'm given so that 53 degrees that I know is part of the triangle, but you obviously could draw it the other way and find that other angle. Now that I have that, I want to find the two sides, and really it's just a matter of doing some trig here, right, using SOHCAHTOA. So this is the adjacent side of the triangle. This is the hypotenuse, so we know that cosine of theta is equal to adjacent over hypotenuse, so I can say cosine of 53 is equal to y, that vertical component, over the hypotenuse, which is 21. All right, I'm going to go ahead and cross multiply here, and I find that my y component is going to be 21 times cosine of 53. So that gives us a value here of 12.6, and the units would be meters because those were the units of the initial hypotenuse. Okay, moving on to the x side, we can go ahead and find that as well. This is going to be the opposite side of the triangle. All right, and we know our hypotenuse, we also know our adjacent, but I'm going to use sine based off the hypotenuse, which is opposite over the hypotenuse. And so we can say that sine of 53 equals this x side over 21. We cross multiply once again, and we find here that x is going to be equal to 21 sine of 53. And we go ahead and calculate that, and we get that x here is equal to 16.8 meters. Okay. Two important things about this. Number one, I'm okay with you just jumping to this point here, okay? Rather than writing out cosine is adjacent over hypotenuse, cosine of 53 is y over 21, you can just jump to the fact that the adjacent side of your triangle, the adjacent component, will always be the hypotenuse times cosine of the angle, and the opposite component will always be the hypotenuse times sine of that angle. All right, so we can make that jump because we are going to be doing these a lot. All right. The one thing you want to be careful of is cosine will always give you the adjacent side and sine will always give you the opposite side. Do not get in the habit of thinking that sine is always the x side or sine is always the y side. That is going to vary. What sine will always give you is the opposite side, the side that the angle is looking at, and cosine will always give you the adjacent. So why don't you go ahead and try the next two problems, pause the video for a second, and then come back and check your work. All right, so for vector B here, for that second question, we have 8 newtons at an angle of 26 degrees north of east. So that means I'm drawing a vector that's going the northeast direction. And my angle here is measured from this east side, and it's 26 degrees north of it. So there's that angle, 26 degrees north of east. Okay, so I'm first going to draw my two vector components. So I have one going east, one going north like that. And now I'm going to go ahead and solve for that. So for my x component, that is the adjacent side, which means that x is going to be equal to 8 cosine of 26. And my y component is the opposite side, which means it's going to be equal to 8 sine of 26. So I go ahead and calculate these, and I get that my x component here is 7.2, and it's going to be newtons because that was the unit of my hypotenuse, and the y is going to be 3.5, and that's also in newtons. And so you see here, we're just jumping right to these 2 points, and like I said, I'm totally fine with that. If you feel the need to write it out every single time, if that helps you out, that's perfectly okay, but it's certainly not necessary. Moving on to the last one here, we have 15 meters per second at an angle of 25 degrees west of south. So I know that this vector is going in the southwest direction. And when I go ahead and think about my angle, it's west of south. So that means we're starting with south and going 25 degrees west. I can go ahead and draw my vector components from there. I have one south component and one west component. Okay, and this hypotenuse here is 15 meters per second. So I can now solve for those two components. So my x component is going to be the opposite side in this case, opposite that 25-degree angle. So 15 sine of 25, which means that my x component is equal to 6.6 meters per second. Okay, because that was the unit of my hypotenuse. And my y component is the adjacent side. So it's going to be 15 cosine of 25 here, which gives me an answer of 13.5 meters per second. For this next one, we're going to go backwards now. So rather than finding the components based off of the magnitude and direction, we're going to find the magnitude and direction based off of the components. So we're first going to draw our two components, draw them tip to tail to put them back together. All right, and then we're going to draw the overall vector. And from there, we can find the magnitude and direction. So for this first one, we have 6 newtons going left and 8 newtons going up. Notice how I line them up tip to tail, which means that my overall vector is going to be like that at an angle, going from where I drew my initial vector to where that final vector ended up. Okay, and now we want to find the magnitude and the direction. So to get the magnitude here, we're just going to Pythagorize this. A squared plus b squared equals c squared. So 6 squared plus 8 squared equals c squared, which means my hypotenuse here is going to be 10 newtons. And now I'm going to go ahead and solve for my angle as well. So to do that, I know 2 of the sides of my triangle. And again, I could use the hypotenuse, but I'm going to use the 2 sides that I know, that 8 and that 6. And those are the adjacent and opposite sides. So what I'm going to say is, thinking about SOHCAHTOA, tangent of theta equals opposite over adjacent. So tangent of that angle there is going to be the opposite side, 8, over the adjacent side, 6. So I now want to solve for my angle. And the way I'm going to do that, right, we can't divide by tangent here. Tangent's not a number, it's a function. The way we're going to do that is by undoing that tangent, by taking the inverse tangent. And there's some information on the next slide about this if you want to get a little bit more in depth here. But the way we undo tangent is we take the inverse tangent. So when I take the inverse tangent of tangent, I'm simply left with theta. And when I take the inverse tangent of 8 over 6, I have tan inverse of 8 over 6, which I can do on my calculator. Okay, I'm just doing second and then tangent. Pulls up that inverse tangent button. And what this does is it undoes that function. Tangent's a function. The way we undo that function and get this theta by itself is by doing inverse tangent. So I end up here with an angle of 53 degrees, and the direction would be, based off of what I have here, I'm starting with the west direction and going north. Okay, so I would say it's 53 degrees north of west. If you drew your vectors the other way, okay, so if you drew it like this and then like that, and you found this angle instead, that's perfectly acceptable. It would just be 37 degrees west of north then. So either one of those answers is acceptable for our direction. So there's our direction there. There is our magnitude. So we would say that this vector is 10 newtons at an angle of 53 degrees north of west, or at an angle of 37 degrees west of north. So go ahead and try the other two, and then come back and check that with the video, and we'll go over them. Moving on to B, we have 10 meters per second east, and then 8 meters per second south. So that's how those vectors would line up. Of course, as always, you can go south first and then east. It doesn't matter. But that gives us our overall angle there, or our overall magnitude, and then our angle. So we're going to go ahead first and Pythagorize this to get the magnitude of this vector. So a squared plus b squared equals c squared. So we have 8 squared plus 10 squared equals c squared, which means that our hypotenuse here is going to be 12.8 meters per second. For the angle now, we're going to use our inverse trig, and I'm just going to jump right to this. Tangent of that angle is going to be equal to my opposite side, which in this case is this 8 meters per second, over my adjacent side of 10 meters. So the tangent of theta is going to be 8 over 10, which means that theta is the inverse tangent, remember second tangent, of 8 over 10. And so I find that my angle here is going to be 38.7 degrees, and that's going to be south of east based on how I have it drawn. The other acceptable answer would be the complementary angle there, which would be 51.3 degrees east of south. So either one of those works for your angle. Move on to my final one here, C. We have 3 meters per second west, so there's my 3 meters per second, followed by 4 meters per second south. I line those up tip to tail. There's my hypotenuse. To get that hypotenuse, I'm Pythagorizing this. A squared plus b squared equals c squared. 3 squared plus 4 squared equals c squared, so c is going to be 5 meters per second. Okay, and then to get the angle, I'm going to say tangent of theta equals opposite, which is 4, because I'm solving for this angle here, over adjacent, which is 3. So that means my angle is the inverse tangent of 4/3. And so that angle ends up being 53 degrees, and that would be south of west. Also acceptable, that alternate answer would be that our angle is 37 degrees west of south. Either one works. So just a quick recap of that one little math thing that we did on the last problem, because maybe you might be a little rusty or unfamiliar with this, but if you're given the equation x squared equals 9 and you wanted to solve for x, what you would do is you would take the square root, because that square there is a function. It's not a number. We can't divide by it. We can't subtract it. We have to undo that function. And so the way we undo that is we take the square root. Okay, that's undoing that squared. Similarly, to get rid of sine or cosine or tangent, any of those trig functions, we use the inverse sine, the inverse cosine, or the inverse tangent. So if we have sine of theta is equal to 0.5, the way we undo that is we take the inverse sine of both sides. When we do the inverse sine of the sine, it basically cancels out, and we're left with theta is simply the inverse sine of 0.5. And the way we get it on a calculator is we just hit that second button at whatever function we want to take the inverse of, sine, cosine, or tangent. One last thing that I want to talk about here, and this is actually going to lead us into the next thing we talk about vectors a little bit later on, and that is the question of, we've done stuff with vectors, but I want to talk about the meaning behind it. So here's the question: why do we draw those vectors perpendicular? So here's what I want you to think about. If we have a person who walks due north, meaning straight in the north direction, how far, for 18 hours, how far did they walk east and how far did they walk west? Okay? And the answer, obviously, is they didn't. Okay? If you're walking directly in the north direction, it means that you are not walking east, nor are you walking west. Another one to think about is it possible to move a box to the right by pushing straight down on it? And you're certainly welcome to try and do this. But spoiler alert here, it can't be done. Okay, you can't move a box left or right by pushing down on it. And the reason for all of this is that x and y are independent of each other. The fancy mathematical term we use for this is orthogonal. So if you would like to impress people at parties, you can use that word. And what that simply means is that whatever happens in the x has nothing to do with the y. Whatever happens in the y has nothing to do with the x. Okay, the reason why we're constantly splitting vectors into x and y is because x and y are independent. X and y are orthogonal. All right, And we're going to take advantage of that, and we'll see in a little bit when we start getting into forces and actually applying this to some problems. But we're going to take advantage of that fact that the x and y are independent and split things into vectors to make our lives a lot easier.